Hi everyone, today we're going to be talking about topic 8.4, acid-base reactions and buffers. So this video is to kind of serve as an overview of all the different kinds of reactions we can have between acids and bases. And so one simple case is between a strong acid and a strong base. Here we have H plus OH minus. Here is H plus, of course, this is our acid. OH minus is our base. When you react these together, you get one product at the end of the day, which is just H2O. And so in any strong acid, strong base reaction, you essentially just get this neutralization reaction. And so if you want to find pH, it's just determined by the excess reagent or reactant. And so first, what we're going to do is just find the limiting reactant, and that, of course, will be completely used up. And then all you need to do after that is find concentration of excess, whether or not that's H plus or OH, strong acid or strong base. Then from there, you can calculate pH directly. Say if you have excess acid, you can just calculate the amount of H plus by doing minus log concentration of H plus. But we can also find POH, which is minus log concentration of OH minus, and then just convert to pH using 14 equals pH plus POH. And so if you have strong acid and strong base, it's quite easy. First thing you do is you just find, to find the pH is you determine which one's excess. Once you determine which one's excess, which you have to do by finding limiting reagent, you assume limiting is completely used up, and it's just the concentration of the excess, which you can use to find pH or POH. So now let's look at the case of we have a weak acid reacting with a strong base. In this case, we have this reaction, HA plus OH minus makes A minus plus H2O. Of course, HA is our weak acid. OH minus is our strong base. This makes conjugate base and water, which serves as the conjugate acid. You can see that this system is under equilibrium. And we have three different cases. One is if you have weak acid in excess. This results in what's called a buffer. And we'll cover that in 8.8. So for now, we don't have to worry too much, but we know that it's going to result in what's known as a buffer solution. And what we use for this is known as the Henderson-Hasselbalch equation, which again, we will cover later. So we don't have to worry too much about it at this stage, but we'll learn how to solve a weak acid in excess. If we have a strong base in excess, all we use is you treat it like strong acid and strong base. You just use concentration of OH minus to find POH. And then again, you can convert from there. And so if you have strong base in excess, it becomes pretty simple because you use up all your weak acid, and then it's just OH minus floating in solution. If you have a weak acid and strong base and they're equimolar, as in same number of moles, in this case, what we're going to do is use an ice table. So similar to how we did in our rice table. In 8.3, you're just going to end up using a rice table, and you find Kb, and then from there we can calculate concentration of OH minus, which can get us to concentration of H plus, and of course from there we can find pH and POH. So there's three different cases we're going to look at here. What you need to look at is which case you're under, and then from there, you're going to proceed in different directions. Again, we'll cover this top case later. Next case we'll discuss is strong acid and weak base. This is just the reverse of what we did in the last slide. Again, if the weak base is in excess, you make a buffer. And we will cover that later on. And again, you use the Henderson-Hasselbalch equation, which we'll be learning in the future. I'm going to just label this HH for simplicity. If it's a strong acid in excess, you essentially use the molarity of resulting solution. You treat it just like the strong acid, strong base of the resulting solution, and you find concentration of H+. Since we have strong acid in excess, this will be pretty easy, and then from there, you find pH. If they're equimolar, then the pH is determined by the conjugate base, or sorry, the conjugate acid of the weak base. So we essentially treat it like this, where we have HB+, this is the conjugate acid. So just the reverse reaction here. Conjugate acid plus water. Since this is, in this case, water is acting as our base, this is going to react in the forward direction to make B and H3O plus, which of course this is just, sorry, let me rewrite this H3O so it doesn't look like a B. And again, this is H plus. And so from there, you can find pH. And so if you have equimolar, essentially, you think of the reverse reaction, and you think of making H3O plus in this fashion. And it'll reach what's known as an equivalence point, which we'll talk more about during titrations. But another way to think of this is just like the weak acid, strong base, you just use a Rice table. And then finally, for our last case, which is weak acid plus weak base, you have HA plus B makes A minus and HB plus, and it's under equilibrium. And so this is pretty simple. They'll react and reach equilibrium, and because they reach equilibrium, you essentially just use a Rice table, and that can get you all the information that you need to find pH or POH. So let's look at this example right here. We have this practice problem where a student mixes 40 milliliters of 0.1 molar HBr with 60 milliliters of 0.1 molar KOH at 25 degrees Celsius, and we want the concentration of OH in the resulting solution. So the first thing we need to look at is what we have. This, strong acid, KOH, strong base. So immediately we know we just have to find limiting, then determine concentration of OH minus. So this is a pretty simple case. And so if we look here, we have 40 milliliters of 0.1 molar HBr. So if we want the number of moles of HBr, that's just going to be 0.040 liters times 0.10 molar. And we can do the same thing for KOH. So the number of moles of KOH is just 0.060 liters times 0.10 molar KOH. This math is pretty easy. We get 0.0040 moles of HBr and 0.0060 moles of KOH. And from this, it's quite easy to tell that our limiting is HBr. Right, this is limiting because we have less moles and they react in a 1-to-1 fashion. And so from here, the math is pretty simple. We know that this is limiting, and so we completely react it. And all we got to do is find the excess amount of KOH. Since they react 1 to 1, you can just subtract them. And so the number of moles of OH minus is just going to be 0.0060 minus 0.0040. And we get 0.0020 moles. Finally, if we want to find the concentration, we just divide this by the total volume, because this is how much the concentration of OH minus that's left over. So I'm just going to do this all in one. Concentration of OH minus equals the number of moles we just calculated. And we divide all of that by the total volume. And so we'll do this in liters. It'll be 0.040 liters plus 0.060 liters, which is just equal to 0.1. Once you do all this math, you'll find that we get 0.020 molar. So our answer choice here is C. So since we have a strong acid, strong base, you just find the excess reagent. And then this is basically similar to a normal dilution problem. Find the number of moles of excess, and then divide it by the volume. Okay, now let's look at the second problem. We have nitrous acid, HNO2, reacting with ammonia, NH3, to make NH4 plus NO2 minus, and the equilibrium constant here is 1 times 10 to the negative sixth. Here, HNO2 is weak acid, NH3, weak base. So essentially here we got to be thinking a Rice table. Right, weak acid, weak base, immediately think Rice table, they're at equilibrium. We're given a value for K. We can calculate some things here. So we're asked, what's the concentration of NH3? Well, first thing you need to think about here is not actually the Rice table, but it's just the dilution, right? Because we've added these together, and so we've diluted them to some degree. We can see that the total volume is just 50 plus 50, which is equal to 100 milliliters. And so now our solution is 100 milliliters, right? We don't have 50 milliliter solutions of each, but now we have 100 milliliters. And so what we need to do first is just determine the new starting concentration of each as soon as you mix them. And that's pretty simple. We just find the number of moles, and divide it by the total volume. And so we'll do it for one of them, but it's going to be the same for both of them because they have the same volume and concentration. But for HNO2, let's say, we do 0.050 liters times the concentration. That will get us 0.01 moles. And then we just divide that by the total volume, which is 0.10 liters. And we get 0.1 molar. And so this is I. This is the initial concentration that we're going to use in the Rice table. You don't use this because that is before mixing. You use after mixing. And so once you've done that, now we can actually use our Rice table. Just going to take the time to write this. Okay, initially I said that the concentration of each is the same because we put the same amount of volume and concentration of each of them. So we have 0.1 for each, and then of course we have no products. These react in 1 to 1, and so for the reactants it should be minus X, and for the products it should be plus X. And at equilibrium, of course, you just add these two terms together. And then we just plug it into our expression for K. K is products over reactants, and we don't have any coefficients here, so it'll be pretty easy. K, which equals 1 times 10 to the 6th. Keep in mind that it's 10 to the 6th. I'm going to rewrite this just because I've written over it. 10 to the 6th, so this is a large K. We can't use the assumption that we were using previously, but this is actually quite an easy problem to solve, and you'll see that in a second. We have X times X over 0.10 minus X times 0.10 minus X. This, of course, it's just, we're multiplying the same thing by itself, so it's X squared over 0.10 minus X that equals 1 times 10 to the 6th. Of course, sorry, there should be a squared right there. Of course, we can just plug this into a calculator, but if we're going to do it by hand, it's quite easy to solve. We're just going to take the square root of both sides. Square root of 1 times 10 to the 6th is 1,000, which is equal to x over 0.10 minus x. If you go ahead and simplify this using algebra, we'll get 1001x equals 100. And then we just divide both sides by 1001. And we get x is equal to 0.0999. Now, we're not done here because this is the concentration of NH4 plus and the concentration of, if we go back, NO2 minus. What we want is the concentration, I'm going to move over here, of NH3, which if we look at our Rice table is right here, 0.1 minus x. So it's equal to 0.10 minus 0.0999. If we do that math, we get that the concentration of NH3 is 1 times 10 to the minus 4. If we look back at our answer choices here, that is answer choice A. This was a bit of a longer problem, but you just need to remember, use a Rice table. Don't forget to start with the dilution first, and then once you use your Rice table, you should be able to get the answer pretty easily, either with your calculator or doing some algebra. We'll do some more practice in class, but for now, that's all. Thanks, guys.